Greetings everybody. Let's talk a little bit about scalar line integrals. Basically, a scalar line integral is pretty similar to what we were doing already when we were just calculating arc length. The only difference is now our integrand is just going to be some arbitrary function, and that function is going to be just a function of just x, y, and z, or just a function of x and y, depending, and our ds is really just going to be our familiar arc length form. So let's say that we wanted to evaluate the line integral over the curve c of x ds, where c is going to be our curve y is equal to x squared from minus 1 to 1, from negative 1, 1 to 1, 1. Okay. So the solution for this one, well, kind of a natural parameterization that we have whenever one variable is just given as a function of the other variable, is just to say that, well, since y is a function of x, we can just make xt and y t squared. So that kind of gives us this natural parameterization in our t values going from minus 1 up to 1. So if we compute our arc length form, our ds being the square root of dx dt squared plus dy dt squared, well, that's going to give us the square root of 1 plus 4t squared dt. And then when we come over and actually compute the arc length integral, or compute the line integral, we've got x ds. Well, x was just our original function for our curve. So x was t and y was going to be t squared. So we just replace x with t. Our limits go from minus 1 up to 1. And then our arc length form, ds, being the square root of 1 plus 4t squared dt. Well, we can just do a u substitution on that one, and we get an answer of 4t squared plus 1 to the 3 halves over 12. Evaluate that between minus 1 and 1, and so in this case we get a value of 0. Computing another one, suppose that we're given a line integral over c for 2x squared plus 3y squared plus 2 ds. And in this case, we want to use the curve c, which is parameterized by cosine t sine t, with t going from 0 to 2 pi. So we're really doing this line integral over the circle of radius 1 for this thing. And so for r prime, so our tangent vector just looks like minus sine of t cosine of t. Our ds, remember, was just the norm of that tangent vector, so that's just going to be the square root of negative sine t squared plus cosine t squared dt, which just simplifies to plain old dt. So now when we compute the line integral, everywhere that we've got an x, we replace it with the x value as a function of t from our curve. So we've got x being cosine of t, so we've got 2 cosine squared, plus 3y squared, well, y just gets replaced with sine of t, so we've got 3 sine squared plus 2, and then our ds, which was just dt. Now it's just a regular integral, and we compute it that way. And kind of going through those steps, we can use our power reduction identities to simplify the cosine squared and the sine squared down to this expression. Doing the integral, we get a value for 9 pi. So we can ask ourselves kind of what would be the geometric meaning of line integrals in this form. Well, kind of one immediate kind of archetype we can keep in mind is that suppose we had a cable that we had varying density for, and that density depended on the position that we were at on the cable. Then we might write something like the mass density for the cable being a form as just our mass per unit length, so m of x, y, z, and then ds being our arc length function. So that if we wanted the total mass for that cable, we would just do the integral, add up all of those infinitesimal little pieces of mass, our m ds over our curve c, and that would give us the mass of that cable along that line. So this is kind of giving us one of our examples of line integrals. So for scalar line integrals, stay tuned next time and we'll talk about our vector line integrals. And I will see you guys